So here's the next video in the Calculus and Vectors course. So this is in the calculus part of the course still. We're going to look at curve sketching, and specifically the topic is going to be on using the first derivative test to find local max and min points. So in order to be able to sketch the graph of a curve, you need to know its local max and min points, as well as we'll talk later about finding points of inflection and intervals of a concavity as well. But this is specifically focusing on finding the local max and min points of a curve using the first derivative test. All right, hope you enjoy. So before we can use the first derivative test to find local max and min points of a function, I need to remind you about how the derivative tells you whether the original function is increasing or decreasing. So let's take a look at this rule here. If f prime of x is greater than 0 on an interval, that tells us that f of x is increasing on that same interval. Another way of phrasing that would be if the derivative of a function is positive, right? This means if the derivative is positive, then the original function is increasing. And below that, the next rule says if f prime of x is less than 0 on an interval, then f of x is decreasing on that same interval. So if the derivative over an interval is less than 0, so negative, so if the derivative is negative, that means the original function is decreasing. So, and I've given you a graphical representation of this below that I'll try and explain to you as well, just to help you remember this, because we need to fully understand how the derivative tells us if the original function is increasing or decreasing in order to understand what the first derivative test is actually doing. So here I've given you two graphs. I've given you f of x equals a quarter x squared, and I've also given you the graph of its derivative, which if we use power rule of derivatives, we'd figure out it's a half x. So we have f of x and we have f prime of x. Well, where is f prime of x negative? Let's take a look. Well, f prime of x is 0 right here, and it's negative for any x value less than that. So f prime of x is less than 0 when x is less than 0. So if I look over at the graph of f of x, what would I expect to see over that same interval? Well, so if I look over at f of x when x is less than 0, what do I notice about this function when x is less than 0? Well, this function is decreasing until we get to 0. And by decreasing, I mean as x is increasing, y is decreasing. Also, I want you to notice that if I were to draw a tangent line to any point on the function when x is less than 0, so like if I were to draw a tangent line to this point right here, that tangent slope would be negative, correct? Let me just draw a tangent slope there for you. So I'll draw a tangent. Remember, a tangent is a line that touches the function at one point in that interval that surrounds it. So there's a tangent slope, and the slope of that line is undoubtedly negative. So if I were to look at the graph of the derivative when x is negative 2, what would I expect to see? I would expect to see a negative y value. When x is negative 2, yes, there we go. I see a negative y value when x is negative 2 on the graph of the derivative. Right? Because this derivative graph, every y value of the derivative tells me what tangent slope I would expect on the graph of the original function. So the fact that when x is negative 2 on the graph of the derivative, the y value is negative 1, right? Another way of saying that, when f prime of negative 2 equals negative 1, what does that tell me about the original function? It tells me that on the original function, at an x value of negative 2, the tangent line to that point would have a slope of negative 1, right? It would have a negative slope. So whenever the derivative has a negative y value, the original function has a negative tangent slope, which means that function must be decreasing. And whenever the derivative has a positive y value, right here it's a positive y value, f prime at 2 equals 1, that tells me that on the original function at 2, the tangent slope would be 1. It would be positive, which means the original function must be increasing there, right? If the function has a positive tangent slope, that must mean it's on its way up. So let's summarize this below a little bit just to make sure you get it. So on this one, when was the derivative greater than 0? It was greater than 0 when x was greater than 0. So over that same interval, when x is greater than 0, I know that the original function would be increasing. Oh, I forgot to write this here. So f prime of x was less than 0 when x was less than 0, right? When x was less than 0, so any part of the function here, the derivative was negative. That means that when x is less than 0, f at x is decreasing. So I hope you get the connection between the fact that the derivative, the value of the derivative, so the y value of the derivative tells you the tangent slope on the original function. If the y value of the derivative is positive, so in this section, that tells me on the original function in that section the function is increasing. When the y value of the derivative is negative, that tells me that the original function is decreasing because all of the tangent slopes would be negative. All right, so I hope you get that connection, and let's use that connection when doing the first derivative test. The first derivative test is a way of testing things called critical numbers to see if those critical numbers are in fact local max or min points. So what is a critical number? A critical number is any value a that is, this is important, that's in the domain of the function where f prime of a is 0 or does not exist. So if we find a place where the derivative is 0 or does not exist, then what we have found is something called a critical number. And that critical number may be a max or min point. And let me demonstrate that to you here with a couple examples. So let's look. Here's a function f at x, and here's the graph of its derivative f prime of x. Well, where's f prime of x 0? It's 0 here, it's 0 here, it's 0 here, it's 0 here. Now, if I look at the original graph, at those corresponding x values, what will I find? So let's notice. So this is about negative 1.5, a little bit more. It corresponds, this point here has the same x value as that x value on the derivative that has a y value of 0. This x value here is 0. If I go to the original function, there we go. And this x value is about 1.5. Go to the original function, the same corresponding x value, the original function is there. This is about a little more than 2.5. It corresponds to this point here. So let's look at each of these separately. So let's zoom in on this point right here first. If I look at that one, the fact that the derivative is 0 at an x value of negative 1 point whatever, that tells me that the tangent slope on the original function, so if I were to draw a tangent slope to the original function at that same x value, it would have a tangent slope of 0. And what type of line has a tangent slope of 0? A horizontal line. And look there. If I drew a tangent slope to that point, it would be a horizontal line. Same with all the other ones. Right? If I were to draw a tangent slope to any of these points, they would all be horizontal lines. So basically, if we figure out when the derivative is equal to 0, what we have figured out is where there are horizontal tangents on the original function. Now, notice 2 of these are local min points. One's a local max point, and one of them is neither a local min or max. So how can we tell from this graph and its corresponding values around the critical numbers what's going to appear on the graph of the original function? So this is why I explained to you about the increasing and decreasing before we started this. So let's look at this first one I've outlined. So this first one I've outlined, notice before the x value of negative, I'm just going to say negative 1.5. I know it's not exactly, but just to make it easy. Before the x value of negative 1.5, the derivative is negative. What does that tell us about the original function? It tells us before the x value of negative 1.5, it tells us the function is decreasing. And if we look over here, yes, in fact, it is decreasing. And then the y values after that critical number of negative 1.5, they turn to positive y values. So since the derivative is positive, that tells us the original function after that critical number is increasing. So the function changes from decreasing to increasing. So if you think about that logically, if a function is decreasing before a point, then increasing after a point, what we have is a local min point. This one here, actually let's do a local max point next. Let's do this one. Let's look at this one now. If we look at this one, let's say it's 1.5 just to make things easy. So x values before 1.5, the derivative is positive. So before 1.5, the original function is increasing. And then after 1.5, the derivative is negative, right? It's negative y values. That tells us the original function is decreasing. So the function goes from increasing before the critical number to decreasing after the critical number. That is going to result in a local max. Notice that this one here is not a local min or a max. How could we tell by looking at this portion of the graph of the derivative that it's not going to be a local min or max? Well, before that point, we have positive y values for the derivative, which means the function is increasing before the point. And then after the critical number, we also have positive y values, which means the function continues to increase. So the function goes from increasing to increasing. So it never actually changes from increasing to decreasing or vice versa, so we don't have a local min or max point. So that's just to outline to you how we can tell whether a function is going to have a local min or max point depending on the sign of the first derivative around the critical numbers. Remember, a critical number is a number that makes the derivative equal to 0 or makes the derivative not exist. I haven't talked about this yet, but I'll just quickly show you an example of what I mean by that as well below here. So here's a function that has a cusp. So for this function, if we look at its derivative, at x equals 0, notice the derivative doesn't even exist. There's a vertical asymptote there. So that we would consider that a critical number, and that may result in a local max or min on the original function. And in fact, it does. There's a local min right here. Another example would be this one. Notice the derivative, it doesn't exist at an x value of 0, but the original function does. It's not a local max or min though, right? It doesn't have to be a local max or min. It just means there's a potential local max or min there. If we look at the original function, we know since the derivative doesn't exist, well, what slope doesn't exist? Well, a vertical slope. So if we drew a tangent line to the original function at x equals 0, notice that tangent line, pretend that's a perfectly vertical line. So, and if you think of this one, the tangent slopes are approaching a perfectly vertical line at that point, right? There's a tangent slope to this point, looks like that, to this point, looks like that. They're approaching it. You can see that what it's approaching is a vertical tangent slope at that point as well. Okay, let's actually use the first derivative test. So what the first derivative test is, it's a way of calculating the critical numbers that are possible local max or min points, and then actually testing around those critical numbers to see if we have a change in sign for the derivative, which would indicate we have a local max or min point. Now this is just going to summarize how we know whether it's a max or a min. So a critical point could be a local extrema, but not necessarily. It would be a local max at a critical point if the f prime of x function switches from having positive y values to negative y values, switches from positive to negative, right? Because that would mean the original function was increasing and then to decreasing, so there was a local max. There'd be a local min if the derivative switches from being negative to positive around the critical number, right? Because that would mean the original function was decreasing and then changed to increasing. There's no local extrema at a critical point if there is no change in sign. No change in sign. So let's do two practice examples of this. So determine all the local extrema for this function using critical numbers in the first derivative test. So remember, a critical number is a number that makes this function, makes the derivative of this function, become 0 or undefined. So we have to start by finding the derivative of this function. So I'll use my power rule to find the derivative of each of these terms. So 6x squared minus 18x minus 24. So this is the equation of the derivative of this function. Now this tells me the slope of the tangent at any point I want on the original function. So a critical number is a number that will cause this derivative to be 0 or undefined, which would tell me there's a horizontal tangent of this or a vertical tangent, right? If I could find an undefined value of this. This is a polynomial function, so we don't have to worry about it being undefined, right? There are no restrictions on its domain. So all I have to do to find a critical number for this function is figure out when is it 0. So I'm going to start by common factoring out a 6 from this. And this is a quadratic that can be factored, x minus 4, x plus 1. And I will get two critical numbers. So how could this product be 0? If x was 4, or if x was negative 1. So I have two critical numbers. These are the critical numbers. if I want to find the local extrema, like these both might be local extrema, or there might be local extrema at those points. I should get the y values that correspond to those as well. So what is f of 4? Where is the original function when the x value is 4? I know when x is 4, the original function has a horizontal tangent, but what's the y value that corresponds to f of 4? So f of 4 equals, if we plug 4 into the original function, if I plug 4 into this function for x, I would get negative 122. And if I plugged negative 1 in, I would get 3. So what I have are two critical points, I'll call these nodes. So these are the critical numbers. These are the critical points, right? 4, negative 122, and negative 1, 3 are critical points. At those 2 points on the original function, there is a horizontal tangent. What I'm interested in, is there a local extrema there? And if there is it a max or a min? So this is where we do the first derivative test. So the first derivative test, we have to set up a chart for ourselves. So for the first derivative test, I'm going to test around those critical numbers. So I'm going to put negative infinity and infinity at either end. And then in ascending order, I'm going to list the critical numbers. And then what I'm going to do is I'm going to figure out what is the value of the derivative within each of these intervals I've created. And what does that tell me about the original function? So let's pick some test values. So I'm going to pick a number between negative infinity and negative 1. So I'll pick negative 2. And then I'll pick a number between negative 1 and 4. So I'll pick 0. And a number between 4 and infinity, I'll pick 5. So what I need to do now is figure out what is the value of the derivative at each of these test values. So where's my derivative function? My derivative function is right here. And I want to test, what were my test values? Negative 2, 0, and 5. So into this I need to test negative 2, 0, and 5. So I need to do, let's do negative 2 first. So it'll be 6 times negative 6 times negative 1. So that would give me 36. So the fact that I got a positive number, I'm just going to write positive here. What does that tell me about the original function in this interval? It tells me the original function in that interval is increasing, right? It's going up, right? Any tangent slope I were to draw on the original function in that interval would be a positive tangent slope, so the function must be increasing. How about when x is 0? That was my next test point. If I plugged in 0 into this, 6 times negative 4 times 1, that's negative 24. So I get a negative answer. That tells me the original function is decreasing, right? Any tangent drawn in that interval would have a negative slope, which means the original function is decreasing. Okay, so at negative 1, the function was increasing before negative 1 and decreasing after negative 1. The fact that it changes from positive to negative tells me there is in fact a local max at negative 1, 3. Right? Because before that point the function was increasing, after that point the function is decreasing. And then at 5, if we plug 5 into the equation of our derivative, 6 times 1 times 6 is 36. So once again I have a positive answer, which means the function is now increasing. So it's going back up. Okay, so that means at the critical number of 4, what we have is a local min point, right? So local min at 4, negative 122. Let's take a look at the graph of this just to verify that we have the correct answer. So let's look at the function. So I've got it typed out here. Here's our function. Notice I've got a local max at negative 1, 3 and a local min at 4, negative 122. Right? And I knew there were maxes and mins from the work we did because we established that before this value, this x value of negative 1, the derivative was always positive, meaning the function was increasing before that point. And then after that point, we established that the derivative was negative, so the function was decreasing. Until after 4, where it switched back to increasing. So that's why I knew there was a min point there. Let's try one more example. So this one, here's our part B. I want to find all the local extrema for this using the first derivative test. So I first need to find the critical numbers of this function, which means find the values that make the derivative 0 or undefined. So let's find the derivative. 4 times a quarter is 1, x cubed. and 3 times 2/3 is 2, so minus 2x squared. So there's my derivative. This is a polynomial function, so there's no restrictions on the domain, so it can't be undefined, so I don't have to worry about that for critical numbers. But it could be 0. So anytime this function is 0, we would consider a critical number, right? Because that would be a place where the function has a horizontal tangent, so that means it may be a max or a min point, or it might not be. But let's check. So let's solve for what values of x make this true. So I could common factor this. I could take out an x squared, get x minus 2. And how could this product be 0? Well, if x squared was 0, the product would be 0. And x squared would be 0 if x was 0. And x minus 2 would be 0 if x was 2. So I have two critical numbers. Let's find the actual critical points by figuring out where is the original function when x is 0 and when x is 2. So let's evaluate y at 0, the original function. So y at 0 is 0. And let's evaluate y at 2, and I believe, so if I plug 2 into this original function, I would get negative 4/3. Okay, so my critical points are 0, 0, and 2, negative 4/3. So these 2 points are potential local max or min points. I know at those points there's a horizontal tangent on the function, but I don't know if it's a horizontal tangent caused by increasing and then decreasing, or a horizontal tangent caused by decreasing and then increasing, or if maybe it does something else weird like this, where there's a horizontal tangent there, but the function didn't switch between increasing and decreasing. So let's go ahead and check and see which of these scenarios we might possibly have by doing the first derivative test. Remember the first derivative test? We need to set up a table and choose our test points around the critical numbers. So negative infinity, 0, 2, and infinity. Negative infinity, infinity, 0, 2. And then I'm going to check what's the value of the first derivative in each of those intervals, and what does that tell me about the original function. So I'm going to choose my test values now. I will choose, in this interval, I'll just choose -1, this interval choose 1, this interval choose 3. And let's check what that does to our derivative. So where's our derivative? Our derivative is right here. So I was going to do -1, 1, and 3. Those are my test values. Let me check. Yes. So -1, 1, and 3. So let's test -1 into the equation of the derivative. I mean, I could do it into this version, this version, this version. Doesn't matter. So -1 into here, that would give me 1 times -3. That's -3. So negative, which tells me the original function is decreasing. And then what happens in the next interval? So between 0 and 2. So between 0 and 2, I chose the value 1. Plug that into here. 1 squared is 1 times 1 minus 2. So that's 1 times -1, which is -1 again. So it's still negative. So the function is still decreasing. So at this x value, the function has a horizontal tangent, right? But before, the function is decreasing, and then after, the function is still decreasing. So we don't actually have a local extrema point there. We don't have a local max or min point. Maybe at this one we do. Let's check what happens after the critical number of 2. So I chose the test value 3. If we plug that in, we get 9 times 1, that's 9. So it's positive. So that means the original function is increasing, which means before 2, the function was decreasing. After 2, the function was increasing. So what we have is a local min at 2, -4/3. And then let's go ahead and take a look at the graph of this function just to verify. So there we go. Let me change my zoom here. Let's do -5 to 5. There we go. Okay, so notice at an x value of 0, yes, there would be a horizontal tangent, but it's not a turning point, right? There is no max or min there. But look here, here's another place where there's a horizontal tangent, and yes, that is a local min. The function was decreasing before that point and increasing after. At 0, the function was decreasing before and still decreasing after, right? Any tangent drawn to any point before 0 or after 0 would have a negative slope. That's why the first derivative had negative values. Any tangent drawn after 2 would have a positive slope. That's why the first derivative was positive after an x value of 2. So that's why we have a local min. It was decreasing, then changed to increasing. Okay, I hope you understand the first derivative test. Pay attention to future videos, and if you watch all of them, you'll be able to do full curve sketching questions using the first derivative test, second derivative test, finding possible points of inflection, and you'll be able to graph any function. So go to jensenmath.ca, get the accompanying material, and make sure you like and subscribe so you can get notifications about any future videos that come out.